You. Yeah, it's bad. Like it's just randomly flickering on me here. It's okay. That's fair. That's fair. All right. Uh, so we're going to talk more about trees and priority queues. We're going to look at the binary tree here, which is a tree that only has a left and right child. Previously, we did an N tree. You have to finish up the one traversal. I was overcomplicating it after I looked it up here. It's actually easier to traverse than I was remembering here, which is pretty handy. Uh, and then coming up, our project, right? We're doing the linked objects. Definitely get started on that early. It's a weird concept. It's not super common, but it's something you want to practice and have done before. Have that toolkit. That will come up again next week. This idea of having linked structures. We'll use it in certain purposes. Usually, it's not all that handy. The linked list itself is really nice if we need good performance for adds and removes. Right. That's what really high performant data structure because I can add or remove in constant time no matter what. I never have the doubling here. So, and looking at which ones we use where. So let me fire up PyCharm here. All right. And open up our project. This should be a recent, right? Uh, trees. There we go. All right. So we were working on this print tree breadth first here. Now, this actually doesn't need to be recursive. So you can do it recursively, but you don't have to. So that was where I was trying to overcomplicate it here. Um, so to print it breadth first, we're going to print this level, and then all of the children, and then all of the grandchildren, and all of the great grandchildren, and on and on and on and on, one level at a time. So to do that, all we need to do is add the children, right? And then process the children's children after that. So we're going to make this list of items here. We're going to append ourselves, right? And then for every child in children, we're actually going to add this one here, and we're sort of going to use this as a queue. We could use the actual queue. Let's go do that. That's probably better here. So let's go add the deck. So from collections, import the deck class here so we can use it as a queue. So we'll make this as a deck here, and we're going to append that one here. And then while the items dot, is it size? Which one is it here? The length of items is not 0. We're going to keep on doing this thing here. So we want to take the first item in there and process it. So we're going to grab the current item for the current tree, right? Essentially will be my items dot, this is pop left, right? Pop left, grab the first one here. And then we're going to print this one out. And then we're going to grab all the children and add them to the queue. So if I've got children, I'm going to add them to the queue. So that way, as I'm looping through this queue, we'll grab whatever's in the first position here, and then we'll process it, we'll print it out, and add them to the queue. So as we go from the top level, we add the top level, and we add 7 children, whatever happens to be here. Each one of those children, if they have children, they get added to the queue at the end of the queue, so that all 7 of those children get printed first, and then all of the grandchildren start getting processed and printed. And if them have children, they'll get added in at the end of the queue as we go there. So we'll take for child in self dot, or no, current tree dot children. So it's where we're working off the current tree. So it doesn't need to be recursive here because we're not going to each one using the self here. We're just saying, hey, whichever thing was left, I know it's another tree because we're a tree structure and trees are recursively defined. Every sub child or every child is another tree. So I can go through and get all of its children here. We're going to, or we can print the item here. So we print the current item, current trees dot, is it data? Is that word? Yeah, dot data. And then we'll go through and take all those children and we'll add them to our queue. So we'll take our items and we're going to append child. That's all we have to do. So we'll add in my children. They'll go to the back of the queue. When I'm done adding my children, we go, is the queue not empty? Okay, take the front one, add all of their children to the end of the queue, this way for your line here, right? And then we're going to keep on going. So that way I hit all of my children in order. And as we're processing them, we all add all of their children. We'll do this one generation at a time, essentially here. So I should be able to print the tree breadth first here. Tree breadth first. this way here, which we should get each level at a time. Oops, string object has no data. Current tree. Really? Top left items. Oh, I shouldn't enqueue the data. Sorry. We'll enqueue self. There we go. Because we want to start with ourselves. Because we want to be the tree here. There we go. That ought to take care of that one for us. And now we get some results. So we get Animalia, Chordata, Mammalia, and then these two were the same level, right? Of the family or something like that, whatever it was. And then these two were the specific species, right? At that same level in the tree here. So we're able to navigate this tree level or breadth first, right? Going wide each level as we go. That's all. So there's different ways of traversing here, right? The depth first was really nice and easy because it was just recursive. Just go and print yourself, go to your child, print your child. Eventually, you'll get to all of your children, and all of their children will be visited, and all of their children will be visited. So there's different ways to traverse trees. These end trees get to be a little bit awkward, right? Where I have some number of children here. So the binary tree makes this a whole lot easier for us here. So I'm going to add a new class here. We're going to look at a binary tree. Probably like that, right? I forget how we do these things. So class for binary tree defines an init here. Now, because we need to know who our parent is, we need to know our children. In a binary tree, you have a left child and a right child. We're going to use linked objects for this. So the binary tree will have this inner private class for a node here, right? And then node then needs to know a couple things. So it needs to know its parent here, so that way you know who your parent is in the tree, right? And then you have a left and a right. You have a left child and you have a right child. And all of these are none until we know otherwise, right? So we'll just assume you don't have one until you tell me otherwise here. So left, right, and none. And all we do is say self.parent is the parent, self.left is the left, and self.right is the right. So it's, okay, whatever you told me, I'm going to store these things here. So when we make a new tree here, we're going to take some data here with our binary tree. This is our starting piece of data here. We'll have what we'll call the root. So our root of this tree here is this main node. So it'll equal a self.node. And, oh, I'm sorry, nodes also need the data, don't they? Data. There we go. And then parents here. So here's the piece of data. And it has no parent. It has no left. It has no right. It's a lonely node. That's all it is here. Okay? We'll add the node. And then we're going to add functions to get the parent, get the left, and get the right. Right? So we can say, here's get parent. It's going to return self.parent. No, not get parent, self.parent. Did I type that wrong? Parent? Oh no, sorry, self.root.parent. There we go, because root is the node, right? My node has a parent here. I'll get the parent, and then we can do a get left, and that'll return self.root.left, and a get right returns self.root.right. Okay, and all of this, if we wanted, we could add the position wrapper. The book loves that position wrapper, where we can interact with given positions, and then they don't ever deal with nodes. It's nice. We're not going to bother with that at this moment here. We'll get to that part later. So I can set a parent, or I can get these parents. I can go and then get their values. So if I want to add a child, right? So I can say I can add left here, given some piece of data. So to add the left, I'm going to go set this as my left child. Now, we might want to check to see if I already have a left child and raise an exception, right? So if self.node.left, right? It's just an if, right? Because if it's not none, this will be true. Nuns are falses, thanks to Python being truthy. Also raise a value error or something. That's fine. Already have a left. Something like that. Child. Okay. Otherwise, then we'll set my self.node.left to a self.node given the data. And then we're going to set ourself as the parent. So I can say, hey, I'm the parent. So I can say, we can even use the named things here to make this cleaner here, setting myself as the parent. So it sets that link here. So it adds this as the left child. So I know I have a left child, and it adds me as the parent. So we're doubly linked, right? I know about my child knows about me. So we're setting up all those links here. We can do the same idea with add right here. You can add a right child here, checking the right here. otherwise raises the value error, sets the node right to the node and the parent itself here. Um, no, shoot, I'm sorry. We could use the position, right? We don't need to use nodes because we want to be more trees. Sorry, we need these ones here because we need to use other trees for data here. Sorry, just the tree itself. So we've got uh, we are the root, just our data is the data, self.parent is the parent. This will be a linked binary tree, right? We'll call this one specific here. Parent is the parent, self.left is the left, and self.right is the right. There we go. And we'll just make, instead of using the node here, we'll just handle it ourselves. This is easier. Then to add the left, right? If we have a left, great. Otherwise, we set left to a new a tree, linked binary tree, given the data, and we're the parent. There we go. This will be a little bit nicer. So this is just a linked binary tree, given the data, and we're the parent. And this way, every child is another tree here. We could use the nodes. That's going to be more work than it needs to be. It's nice when we get to be positional, but we don't need that at the moment here. All right, so I can get the right and get my parent, get the left. So this way, these all return trees here. Um, then other things we know we can add in here. If you don't have a parent, we're going to assume you're the root node, right? So we'll define use root here. So if self.parent, or if self.parent is none, or really we can just return this one here, right? Return it's none. If it's none, that's true. If it's not none, it's false. We'll return a true, we'll return a false here. Okay, we can have a is leaf here. We talked about this idea if we don't have any children here. So we're going to return self.left is none and self.right is none. If both of them are none, we must be a leaf node. We don't have any children left, right? And then we can have a get children. This one gets to be a little bit weird. We use this fun yield keyword. So actually we need to check. So if self.left, right? If it's not none, we're going to yield self.left. And then if self.right, yield self.right. So this idea, I can put a tree in a for loop, right? And get out or I can put the get children in a for loop and say for child in get children here. And as it iterates over them, gets the first item, it gets the first thing I yield. And then it sits and waits and remembers where I left off here. So at the end tree, right, I could give one child at a time. I could yield each item at a time. So to put it in a little for loop is nice. We get the children, we get the left, we get the rights, add that here. Cool. So we should be able to make a linked binary tree now. So here's, and we can do that same kind of structure. We'll do something else here if we're doing just a binary tree. How about we have like items here? So maybe we'll have classifications for items. So we'll say this is my items tree is a linked binary tree, and the first top level is just item here. And then sub-classifications of items. We'll have taxable items and non-taxable items if we wanted to. So you can say, hey, items tree dot add left here will be another, this is non-taxable items here, and an items tree dot add right will be taxable items. Okay, and then my left tree is my items tree dot get left. Right now in the left tree, I can add a left child and a right child. So to take my left tree, I can add left. So for non-taxable items, we don't tax, what is it, essential goods, foods, isn't that? Non-prepared foods? Is there a word for that? It's non-prepared foods. Groceries. But not all groceries. It's not all groceries though, right? Isn't it like only certain categories of groceries? I don't know. Our tax system is crazy. Left tree dot add to the right. And now also we have hygiene products have been recently added, at least in Michigan. They're not taxable here. Did I spell that wrong? I did. Place. Okay. Taxable items then. So my right tree is my items tree dot get right. Here we can go and add right tree. Why did I do a capital T? Right tree dot add left. So taxable items here are everything else. But if we want to have other categories here, um, how do we want to classify those? We could break them into, say, items that we sell extended warranties for, right? That's a big sales pitch here. So your store wants to know where we can offer you those extended warranties. They come up on the weirdest things at Target. Like, oh, do you want an extended warranty for this kid's toy? Like, depends on what it is here. Like, yeah, it's an extra dollar, right? And then a right tree at right, we might add um, cheap things you'll have to replace often. I don't know. Whatever we happen to do here, we can come up with whatever we want here. So to print this out, we get the same idea here. I can either print one level at a time, or I can print that breadth first. I'm sorry, I can go depth first, print, go all the way down to the child here. Uh, Now you can also, depending on how we structure this, we can traverse it in order, which gets to be fun. So it doesn't make a lot of sense until we sort these. So we'll get to that when we get to our binary search trees, which means they're going to be in sorted order. So that's a whole other topic. We can do those sort of traversals when we get to search trees in 2 weeks. So this is just the basic tree structure. So one of the cool things we can do with this basic tree structure of being left, and having right here is we can make what's known as a priority queue. These ones are a lot of fun, and I love priority queues. It's a fantastic data structure. So this is our priority queue. Now, they do with the priority queue is our easiest example of that is the emergency room at the hospital. If you show up and you've got a broken leg, and someone else shows up and they're having a heart attack, they're going to take the person with a heart attack first. Your broken leg hurts, but it can wait a little bit here. If someone shows up and they've got a cough, they're probably the end of the line, right? So you do these things in order of priority. However, we want to define priority, we let them be at the top of the queue. Um, So to do that, we need items to be sortable. I have to be able to compare items, say, hey, this one's greater or this one's less than, whichever one you can do a max priority queue or a min priority queue. Either one you want to implement is fine. So we'll have this, should we do the max or the min? We want like the highest number should go first, maybe? Do a max priority queue. So the max priority queue then stores itself as a linked binary tree, which gets to be really cool. So we're going to store all of our data in this tree structure here. Uh, So for our priority queue, we're going to define our init. Uh, Probably take the first piece of data as we go. Right, we'll probably take some data here, and then we'll say self dot. Oh, I got to go import here from binary tree, import binary tree, linked binary tree. It could be a tree itself. We could use inheritance. We don't have to. We can store that separately here. You got lots of different ways of going about it here. Uh, I think this is probably fine going about it this way as we go here. Um, so we'll take some data. So we'll say, hey, the root here is going to be a binary tree, a linked binary tree, given some piece of data. So if there's only one thing here, it's the top. It's going to be the most priority here. So now things we get to do, we can get the max item here, get max or something like that. So we're going to return self.root.data. Right, here's the data at the top here. You can remove, right, remove max here, which is going to give you back that piece of data and remove the item from the tree, or just remove it from the tree, whichever one we want to do here. So this one's a little trickier because we have to figure out what replaces it here. Or we can add some piece of data. So we'll come back to remove in a minute. So adding a piece of data here. When we're in this tree structure, the priority queue has a rule. This is how it keeps itself ordered and makes this be pretty quick here, is it's going to make sure that the children are always less than the parent. Because if we want the parent to be at the top, or the maximum number to be at the top here, if you're less than, then you have to be a child. Right? You have to be a child. Um, oh, we could do the bad. Do you want to do a bad implementation of this before we do the tree? That's a waste of time. So if you make this in a list, you just have to scan the entire list to find the max thing and then remove it. That sounds really slow, right? Like if I just put them in a regular list, I have to look at every single item to find which one is the biggest, right? Or I could put them in a sorted list and keep the list sorted every time. Then inserting gets to be really slow because I have to find the right position to put this thing in. right? So it's still, I'm going to look at maybe n things to find that here. So that should have started with the premise here. I'm really sad about my laptop, and it threw off my whole day. Sorry. Um, so in terms of being fast and slow, using a list to make a priority queue is really slow. Right? So we're just going to skip it and say, no, we can do better, because smart people have found out we can do better. So the priority queue, what we're able to do is get logarithmic performance, log of n, which if you know anything about logs, right, because you're all smart math people, logs are way faster. Right? Log of n is immensely better than n performance. At least when we get, big items here, we'll be a whole lot faster. So to do that, we put the top item at the top, the biggest item at the top, and there's a process we call down heaping. I love down heaping. It's a fun technical term here. So we're going to put it down where it should go here until we find the place that it belongs in the tree here. So to down heap, then we're going to go add this piece of data. We'll call self.down heap the data. Okay. I guess that's fine. So we can down heap, and then we're going to start at self.root. So we're starting at the root here for this down heaping process. So to do down heaping, this is going to be a recursive process. So we're going to define a down heap process here that takes some tree here, right? So if the tree is none, actually we don't even, we should never have root being none, right? I guess we need to check for that. So we can check if self.root is none, then we'll go and set self.root is a linked binary tree with that piece of data.
But if you have an empty yard, that's
Yeah. So if we've taken the last one off, we could be empty. So if we're not empty, then I need to find out where this thing goes here. Okay. Uh, so when we down heap our items here, we need to check to see, does it belong at this level or not? Right. So if it's less than here, then it needs to be a child. If it's more than this tree's data, it needs to become this tree's piece of data. So we'll check, hey, if the tree dot data is less, oh, sorry, we need that data too. Shoot, the piece of data that we're adding in here. Here's the data. Yeah, and the root. Yeah, take the data and the root. So maybe we'll say if the data is greater than the tree dot data, then I need to go here, right? And that piece of data needs to go lower, right? Because I need to be in its spot. So we can move that piece of data further down somewhere else in the tree. So as we're going, if we can move it down, if there's an open child spot, we just put it in. So if we're greater than, we're going to check to see if the tree dot left is none, then we'll make tree dot left equal, oh no, tree, it's the linked tree. Yeah, tree dot left equal the linked binary tree given that piece of data, and then its parent is now going to be the tree here.
Does it matter if you were to put left or right?
We're going to check left first. We just need to do one particular order. So as long as we're doing it the same order, it should be fine. So if the left is none, we'll go add it as the left child here. I'm sorry, this is if we're greater than, shoot. So if we're greater than, we want to move the tree data down to this spot here. And then we replace the tree.data with ourself. Right? So we'll swap in our piece of data for what was there and move that piece of data down. So if we want to like draw a little picture of it here, it says, hey, say I've got like a 10 here. Is that working okay?
I have black. Black.
Oh, yeah. In dark mode, it inverts the colors. So if I turn off dark mode, it'll look normal. So we don't have any children right now. So if I'm going to go add something and it's greater than, we'll say, okay, well, let's move the 10 down here. We'll put 10 down here. And then we'll swap out this, same way we were putting in a 15. Right? Now, if we're not greater, then we need to become one of the children, right? And see where we go in this process. So if the left is not none, then we can check if the tree dot right is none. Then we can do the same idea here. Tree.right is a linked binary tree, given the tree data, and the parent is the tree here. Tree.data. And then we swap this one in here. This is a little bit messy, but that's okay. If we did that, then we can return. We're done, right? We don't have to do anything else once we swapped. If we do this one, we can return. We're done. We don't have to do anything else. If we're not greater than, then we have to become one of the children. We have to see, hey, is there an empty child here? Um, so we need to sort this into the correct position as we go.
Right. The water replacement.
And we're taking the new data, putting in the tree's place, and then we're moving it down one as we go. Uh, yeah, does that make sense? We're checking those two as we go. So if we're greater, we need to swap. If we're not greater, then we need to go lower. And technically, equals is okay. We'll just put them one lower as we go.
Oh, so the equals, it pushes it into the tree, doesn't delete what it's.
Yeah, so either way you set it, usually you can handle equals, you can handle multiples in a priority queue. You can have exclusive ones if you want here. That's getting too big there. This screen is driving me crazy right now. So we can move this down into position as we go. So we checked. We don't need to swap. So we need to go and look then, hey, do we belong somewhere else? Right? So we're going to go and check to see, hey, can I go to the next level and put myself in there? So we want to then, we're going to check, we want to use the children. So if we're otherwise, then, so we didn't swap either of these, we need to go and try and check. We know then that it has both children, right? So if we are less than the children, right, we can keep on repeating this. So if the tree.left is there, we're going to repeat this process. So we'll call self.downHeap given the piece of data and then tree.left. So we'll just repeat this process on the left here. We can just return that, right? Because that should finish it off when we're done. Eventually, we'll find ourselves in a free spot here where we've got an open position and then we're greater than. I'm really off today. I'm sorry, folks. Because eventually we want to find ourselves. This is for greater than. So if we get to the point where we find one that is none here and we're greater, we can swap. That's fine. So we're not swapping. Then we're checking to see for the children. So if the tree left is there, if it doesn't have a left, right, then we can become the left child at some point in here, right? So if we're less than, this is if we're greater. Also, if we're less than. Oh, okay. So if the left is none, there we go. If the left is none, then we put ourselves in the left here. So then tree.left equals a linked binary tree given the piece of data. Its parent is the tree here. Okay. If the left isn't none, then we can also check then return. Well, so the else case should be we're less than, right? Because if this is true, we've got to be greater than. So if we're not greater, there's no swapping that has to happen. Now we need to become one of the children. So we're going to check, hey, is there room in the left child? Great, let's do it. If we didn't return there, we'll check the right child. If there's room in the right child, set tree.right to the linked binary tree, given the data, and the tree is the parent, and then return. So if there's not room in the right or the left, then we can go and move ourselves into one of the children. Here's we go.
In this case, we're assuming there's no equal status.
Equal should be okay because we're not greater, so we didn't swap. So we'll become a left or a right child.
Okay, all right.
As soon as we find an empty spot here.
So just becomes next regardless.
Yeah, it'll filter it down into the process here. Uh, so we can find out where this one belongs as we go. Should be able to downheat. What is it yelling at me about? Oh, because I never finished remove max. So removing the max gets to be a interesting process because the idea is we're going to remove the top node. We need to put something else in its place as we go here. So what we need to do is put something in that keeps us in this tree form. So when we talk about trees, there's a couple definitions we can look at. So with a binary tree here, you can technically look like this here. This is a binary tree, technically. I only ever have right children. Sure, technically a binary tree. That's a B there. Goodness. B tree. It's the terrible one, and it's not going to be very efficient here because I'm only using links to the right. But you can. You're technically a binary tree. Um, so when we work with trees, one of the things we want to do is try and be in more of a balanced form where we've got close to equal number of children on both sides here, right? As you can see, this one is a binary tree, but it's not very balanced, right? Because we got way too many nodes over on the right-hand side here. So it'd be nicer if we move some of those nodes to the other side here and, take advantage of having all of these children positions rather than just chaining them off the side here. So when we look at trees, trees have a height here. So the height of the tree, is that an E or an I? I'll just say H here, right? Is how many levels it has here. And then you can talk about for a particular node, what is the depth of a node? How deep is that node in the tree? Right? Kind of what level is it at here? Is it 0 for the root? Is it at level 1, level 2, level 3? So nodes have depths. A given tree has a height here. What's the height of a tree? And then when we're putting these things into these binary tree structures, you can be a full tree if every level has children, right? Or full. Because every level is completely full, right? This is pretty good here because this will be the most balanced when you're full. Right? We're not going to end up with all these children hanging off of one side here, and we won't be in a very balanced form. Where's my scroll wheel not working? Right. The other thing you can be is you can be a complete tree where you're not quite full, but every level except the last is complete, is full. And then as you're adding nodes, you add them to the far left. So nodes always going to be added to the next available spot in that generation. So from this one to this one to this one to this one here. So it keeps us in a complete form here. We're almost full and we're working on being full. So what we want to do is as we add and remove nodes, we want to fill up next individual spots in each of these here. So you're able to go and say, okay, where's the next available spot here? I need to put myself in that location here. So if we can get to this level here, what you're going to do, let me do another page here, right? Imagine our priority queue where we started adding patients in here, right? We've got the most priority at the top here. We're doing numbers, right? So let's go with like 20 at the top here. And we have a 10 over here and say like a 15 over here, right? As we go add more data, we want it to be the last available spot here, right? So add it into the last spot down this way here if it's less than. If not, we want to swap 10 with whatever's over here. So maybe this becomes an 8 here if we're going to add that one in, right? We're going to be less than. If we wanted to add another number here, right? The rule is I have to be less than my parent as I go here. So if we're going to add, say, like a 12, right? If we wanted to add the number 12, we're going to look at these. Oh, well, I need to go in the next available spot over here to start, right? So we'll put it in the next available spot here. But now I'm violating that rule, so I have to swap myself with my parent here. So we're going to swap out, okay, let's swap the 10 and the 12 as we go here. So we'll put the 12 in this place here, put the 10 over here, right? If I want to add another value, say we wanted to add like 13, right? It's got to go in this next available spot here. So we need to put the 13 in here. And then we need to check, hey, is it in proper position based on our rules here? Is it less than your parent? Yeah, that one's fine. It can stay. How about like an 18? Okay, we want to add to the next available spot here. We'll put an 18 in. Does it follow the rules? No, it doesn't follow. So we need to swap. So we're going to swap 15 and 18. Oops, I lost my circle there. 18 and 15. And then we check, hey, do you fit? Right? Do you follow the rule? Are you less than your parent? Yes, we are. Okay, we can stop swapping here. So if I add, let's say, a 40 here, I'm going to add it to the next available spot here. We'll add a 40. Wow, 40 was hard to write in there. Sorry. 40, 40. And says, okay, are you less than your parent? No, let's swap. So we swap the 8 and the 40. Right? We put the 40 here, the 8 over here. It says, okay, are you less than your parent? No. Okay, so you swap. So we're going to swap again. So we swap the 12 for the 40. Put the 40 in here, swap the 12 out. So, okay, are you less than your parent? No, we're not. Okay, so we're going to swap again. So take the 40, swap it with the 20. Okay. Along the way, as we're going, because we're always taking a number bigger than us, we know it'll be fine for our other children. Right? I don't need to worry now, is 10 going to be less than that number I just put in here? Because I know I'm less than my child. I'm less than my parent. So my parent had to be bigger than me when I did that initial swap. So if we can find this next available position, it's really easy to add it in and do all the swapping. I don't have to look at lefts and rights. I don't have to manage all these sorts of things here. Um, so the fine folks who invented is probably the right word here, or came up with this concept said, hey, links are great and all, but couldn't we do something easier? Is trying to find the next available spot's really annoying, right? Because then I have to traverse all of my links here, and we could, but it's going to take a lot of energy and effort here. So trying to manage this left and right nonsense is just not friendly at all here. It gets to be really ugly this way here. So we can do better with a priority queue and not use links. So I'm actually going to throw away all of this stuff here. So the max priority queue linked here. Um, I'll leave it all there. So this is throw away, because it's workable, but it's awkward here. So the easier thing for us to do here, if we have this kind of complete structure, thanks to math, you all love math, I'm sure, right? And your discrete structures and those sorts of things here. You notice how many items are at each level, right? Well, there's one item, and then there's two items, and then there's four items, and then there's 8 items, and then there's 16 items. Does that look kind of familiar? Right? That's the powers of two.
Yeah.
Right? We're just doubling each time. So if we were to take all of these values here and throw them into a list, we can find your child and your parent with some arithmetic, thanks to the powers of two, which is really fun. So if we were to look at this and say, hey, this is index 0, this is index 1, this is index 2, this is index 3, 4, 5, 6, 7, on and on and on and on. As you go here, right, you're going to put all these values in a list here. So we're going to have 40 at the front here. We're going to have 20. We're going to have, is that 18? Right? We're going to have 10. Or was that 12? Might have been 12. 12, 10, 13, 15, 8. Now, finding the next available spot here is super easy because it just appends to my list, right? Which we know is super fast. Just go add to my list here. So I can add it in the end, and instead of having to downheap and figure out, well, where does this go shuffling it downward, we get to do the opposite. We get to upheap, which is my other favorite technical term, upheaping. It's much prettier than it sounds. So if we have that sort of tree, this is our max priority queue list based here, right? We're going to define this init. So we're going to have a self.data is a list here, and maybe we take the piece of data first. We start with the piece of data. Sure. So to define the get max here, well, we know that's always going to be the front here because we know we're going to keep that on the top. So we're just going to return self.data at 0. How fast does that run? That's constant, right? We can get the first one here. So then to add some piece of data here, we're going to take my self.data, we're going to append that data to it, and then we're going to upheap it. So we're going to define a upheap process here, given some index here. Okay, so then we'll add it to the end here, and then we'll upheap it, self.upheap that the index, where it is then should be the length of self.data minus 1. Right, that'll be this position we just put it in here. Should be fine. So we can upheap. And actually, we can start this off. I think we can be empty. This might even be easier here. So we'll just start empty, and we'll just let them add as we go, because then I don't have to have special handling for if I'm empty or not. So when we upheap, then we're going to append it. If the index is 0, we're done. Right? If it's 0, there's nothing to do. So really, if it's not 0, not equal 0, or say if it equals 0, you just return. We're done. That's our base case. This upheap is going to be recursive here. We need to figure out what is that arithmetic then to get between these indexes. So this is 0, 1, 2, 3, 4, 5, 6, and 7. So we know that if we were to like draw this out as a little table here, um, the index here, I guess we'll just do I, right? Your index, right? And then your parent's index. So if your index is 0, you don't have a parent, right? That one's fine. But index 1 and 2, its parent is 0, right? Indexes 3 and 4, right? If we look at our tree here, this was 3 and 4, its index was 1, right? You can say, okay, that's 1. Indexes 5 and 6, its parent index was 2, right? 5 and 6, its index was 2. Indexes 7 and 8, here then, its parent would be 3. Right? Let me make some more room here. Kind of erase some of that garbage. So 7 and 8 was 3. 9 and 10, right? Its index would be 4. Right? 11 and 12. You kind of see the pattern going here, right, as we go. So what arithmetic can we do to get your parent's index? It's sort of a thought exercise, but sure. What if we take the index minus 1, that should be I, right? And then floor divided in half. Does that get us the right number? So 1 and 2 become 0 and 1 divided by 2, no floor division, 0. 3 and 4 become 2 and 3, floor division, 1. 5 and 6 minus 1 becomes 4 and 5, floor division, 2. Right? We'll take 1 away, floor divide by that. Now, it doesn't really work with 0, but that's okay. Not the big deal here. So what we can do is we can add a little helper function, right? So define get parent index here, because we love functions here, right? Given an index here. So we're going to return index minus 1, floor divided by 2. But make sure we force some order of operations here, right? Minus 1 divided by 2. So if the index was 0, there's nowhere else to go. There's nowhere else to upheap. There's nothing to swap with. Other than that, then, we can check. We'll say, hey, if the self.data at the index is greater than the self.data at the self.getParent up index of the index, right? Are you greater than your parent? If you are, we're going to swap places, right? So we'll have temp is self.data at the index, and self.data at the index then becomes the self.getParent. I guess should we define that then, parent index? Because we're going to do that more than once. Let's do that. Right? Becomes the parent index, and then, self.data at the parent index, and then self.parent index, data at the parent index becomes the temp. Right? You can technically do this in one line in Python, but I hate it because it just looks really awkward. You can assign two things with two separate two things, and you don't need to deal with the temp. That's what the chatbot will give you all the time, right? It looks like self.data at the index, comma, self.data at the parent index equals self.data at the parent index, comma, self.data at the index. This is super ugly. And like, I don't know, it just looks awkward to me. I don't know. We'll leave it there for reference. So, again, chatbots loves to be efficient, copy off of smart people's code. So, sure. I think this just makes more sense. So if we're not greater than our parent, we're done here. We're fine. If we are greater than our parent, we swapped, and then we're going to recurse. Return self dot upheap. Actually, we don't even need to return anything, right? We just finish. So then call self upheap at the parent index, right? This is my new location. Repeat, recurse. Okay, if it's 0, we're done. Otherwise, go do this stuff here, right? I guess we can move all this into saying if we're not 0, do all this here. Is that nicer? I don't know which one you like. This one has everything indented a little bit more here. Sure. So if we're not 0, recurse, swap and recurse, swap and recurse. As soon as we're no longer greater than, we don't need to move anymore, right? We're fitting the rule here. So this way, we put it in the last node and we just keep on going, right? So we can add something. So we get the parent index. Yeah, but it doesn't technically need self here because we're not using the self attribute. So that's the suggestion, make it static. We didn't spend a whole lot of time with static. We talked about it a little bit with classes. They don't need self attributes. You get one definition of it here. It's kind of defined at the class level. It's okay. So we can do that. So we'll upkeep that as we go, right? Just keep on moving it up and moving it up, moving it up, moving it up, moving it up. So now removing something here, if I want to remove the top item here, if I want to keep my complete form, we do the opposite. We're going to take the last item off of my list here, whatever the last item is, put it in this place, and then downheap it. So this downheaping, we'll just keep putting it lower and lower and lower and lower as we go. Working towards the favoring the left side, right? Because we need to make sure we're adding to the left wherever possible here. We'll just keep on going that direction as we're going. So we're going to, or no, if we take it off, yeah, we'll just filter down to where it needs to go. So when we swap with downheap, the only piece we need to do is make sure we take the largest child here because we can't take a smaller child. So if I were to swap out, so when we take off the max item here, like 40, we'll get rid of it here, and we're going to swap it with the smallest child. We'll say 8 at this point here. We'll put an 8 in here. Now, all we need to do is replace with the largest child because I can't put a 19 here because then 20 is bigger than it. It's not going to fit the rule. But I'll take the largest child. So we'll swap now. We'll downheap, swap 8 and 20. Here's the 20 now, and the 8 goes back here. Now we say, okay, swap with your largest child, 12 or 10. We're going to swap with the 12. Right? So 8 goes here, 12 goes here. There's no more children. We're done. Right? We don't have to do any swapping. Okay. So we can do that. So for down heaping then, so to get the max, and then we wanted to like have a remove max, right? Remove max, or just remove maybe, right? Because this is, we know we're a max priority queue. When we remove something, we're just removing, we'll know it's the max here. So we'll have the data is self.data at 0 here. Eventually we're going to return that data, right? In the meantime, we need to go and do that swap. So we're going to pop off the last item of our list here and put it in place of 0. So self.data at 0 equals self.data.pop. Take the last thing off, put it in the first index here. Then we're going to call self.downheap starting at 0. Right? Eventually, we can return that piece of data. So then downheap needs to go and figure out how do I replace myself with my largest child. Downheap, given an index here, right? Just always based off of indexes. So looking at children then, how do I get a child index from a given index? So we can kind of go the opposite direction here. So from 0, my left child is 1, my right child is 2, right? So let's kind of sketch this one out here. So we'll have do a 3 node here. So we'll have the index, we'll have a left, and we'll have a right. Okay, so at 0, we've got 1 and 2. At 1, I've got 3 and 4. 3 and 4. At 2, right, I have 5 and 6. Okay, at 3, I have 7 and 8. Is that enough to see a pattern? I need to keep going. So my sketching here is really bad. I'm sorry. I got to bring in my tablet. So it's my index times 2 plus 1 for left child, index times 2 plus 2 for the right child. Right? So at 0, double it, add 1 for the left, add 2 for the right. At 1, double it. 2, add 1 for left. 3, add 2 for right. 4. At 2, double it. We're at 4, add 1 for left, add 1 for right. Right? I think the pattern holds up thanks to the powers of 2. We love powers of 2, right? We multiply by 2 or we divide by 2. Right? We're just doing that little shifting here. So I can get a left child index, right? So we have a fine get left child index then, given an index. Now, we're going to calculate it here, and then we're going to return it. But we also want to check to see if you actually have a left child or not here. So we'll do the calculation. So the left child index then will equal index times 2 plus 1 here. But then if my left child index is greater than or equal to the length of self.data, I'm going to return none. Right? You just don't have one here. So I'm going to give you back a none here. Otherwise, then we can return the left child index. So this way, when I go and get it here, I can see, do I even have a left child or not as I go in here, right? Same idea with the right child index, right? We'll just change our arithmetic a little bit. Get the right child index. The right child index is that plus 2. And check, is it actually a valid index or not, right? Do we actually have one here or not? So as we go down heat, we're going to check and see, hey, do I have a right child and a left child, right? If I don't have any children, I don't need to move anywhere. No swapping has to happen, right? So if my self.get left child index, given the index, and self.get right child index, given the index. So if either one of those is true, I have work to do. I'm sorry, if both of them are true, I want, if either one of them is true, right? I have work to do because I have to go and look. I might have to swap, right? So if I have a left or I have a right or I have both, right? Both of these cases will be true here. Then I need to go and look and see which is my largest child. So I know I at least have a left. I may or may not have a right. So my largest child will equal, I guess we should grab those indexes, shouldn't we? So a left child index is self.get left child index. Let's do that. And then a right child index is this one here. We'll swap that out. Otherwise, I'm going to have to call that function a whole bunch of times here. So self.data at the left child index, we're going to assume is the largest one, right? Then I can check, hey, if, I'm sorry, the data there, specifically the data, right? I grab the data out of that one. Then I can check, hey, if I have a right child index, right? Then I'll go see my largest child, if my self.data at the right child index is greater than the self.data at the left child index, right? Then my largest child will be the right one, right? Actually, no, sorry, this right child index. We'll compare indexes here. There we go. This will be a little easier. So we'll just say, hey, the left child index, if the data is greater than the data at this one, then my largest child index will be the right child index. It's a little awkward looking. I guess we can even do this with an and, right? So and this one here. So if we exist and we're larger, here, let's save a little bit here. Okay. So if I have children here, then my largest is the left. If I have both children, then if the right is bigger than the left, the right's the biggest one. Okay. Then I need to check, okay, I know which one the largest is if I need to be swapping here now. So if the self.data at the index is less than the self.data at the largest child index. What's it not like about that? Oh, sorry, if I've got children. I'm still inside of this if block here. So if I'm less than, I need to downheat. We'll go and swap, right? And again, we've got this swap code. We've got it more than once. We could go pull this out, right? So let's go take this bit here, and I'm going to right click and go extract, or is it refactor, extract method here. We'll call this swap as a private swap. Swap here. So we've got a little helper function for swap. Where did I put it here? Put it down below, right? It'll do the swapping for me, just so I don't have to repeat those same lines of code here. So if I'm less than, I need to swap. So self.swap my index with the largest child index. then we repeat. We recurse self.downheap given the largest child index. We just keep on going. So it's going to filter us down. It's going to downheap us in this structure here. We use the word heap because this is known as a heap. So I probably should have started with that too. This particular structure we'll call a heap. Unrelated to other heaps. I don't know why they call it that. That's a fun technical term there. So this way, now we have a nice, quick, recursive form. I don't need to be checking all these links in my left and my right, but it only really works if we're keeping that complete form where I'm always adding to the very last position here. If I'm adding anywhere and you can add a right child off of like the rightmost node, none of this arithmetic works, right? Because I'm not going to have those items here. I'm going to have a bunch of gaps and you can't add things here. So we're taking advantage of the fact that we're a specific binary tree kept in complete form. We can do this with a list. The basic trees, we can't do this. Or maybe we could, we'd have a whole bunch of holes, we'd be wasting a lot of memory doing it that way. Because if I had a right and a right and a right and a right and a right of like 20 of them, I'd have 2 to the 19th open spots to store 20 things. The math gets real bad real fast. So really, we only do this because we know we're keeping that complete form with our tree. Makes life kind of easy for us here. So we get the max, and then we've got our little helper functions here for downheaping. What is it? This typo in word downheap? What is it? Sure, that's fine. I probably spelled it wrong, but that's okay. And upheaping, right? We do our swaps, and then we recurse. There's our swap. We can add something. So here is our max priority queue with a list. Math works out really well. So when we look at how fast this stuff performs here, this is constant here. The helper ones, this arithmetic, right? That's constant. It's always the same arithmetic, no matter how many n items I have here. O of 1 for the get right child index, that one's constant here. For downheaping. Now, if we're in that complete form, right, then the most work I'm ever going to have to do in my worst case performance is I'll have to start from the top and downheap this level, this level, this level, this level, this level, this level, this whatever it happens to be. But we know the number of levels is related logarithmically to the n size. Right? We looked at each because each level doubles here. So the performance for this one then gets to be O of log n. Here we're finally doing something faster than n, which we've never been able to do before. We've either been constant or n, right? Now we're in that sweet spot kind of in the middle, and it can be log of n performance-wise. Is way better than n. So if I've got 10 million things here, and most it's going to take me, what, like 10 operations, right? Is that 2 to the 10th or something like whatever happens to be? Or you can get to 2 billion in 16. So um, math is not my strong suit, unfortunately. Here, yeah. So if you've got 2 billion things here, I'm only going to have 16 levels of my tree here, right? So with 2 billion items, being able to do this in 16 operations is immensely faster than if I had that list of 2 billion things. I had to look at 2 billion items, right? So downheaping is super fast comparatively, right? It's not constant, but it grows very slowly, which is nice. Remove, then, because it uses downheap, right? This one is O of n, or O of log n, right? Constant to get the data, log of n to downheap, right? Get the parent index as constant, O of 1, upheaping, right? Taking that item and swapping it up to where it needs to go here. Again, level-based, right? If I add the biggest item to the bottom of the tree, it just has to work its way up every single level. So average is still log, right? Because we don't know where it's going to be in average for the number of n items here. So average and worst case are still log of n. Best case is it never moves at all and it's constant, but no one cares about best case because you're not going to get the best case most of the time here. So logarithmic n for upheaping, which means adding something is logarithmic n. Right? O of log n. O of log n. There we go. Log n. Right? So when you add something, because we're upheaping, it's logarithmic. So I can have my 2 billion items and at most do 16 operations to add this thing in and keep it in a nice sorted order here, which is cool. Swap is constant, right? This is O of n here. O of, I'm sorry, O of 1 for a swap, right? This is 3 operations no matter what. Grab the temp, swap the 2 things, always, no matter how many n things I have. So the other fun thing we get to do now is I can use this max priority queue to sort things here, if I wanted to. Now it's a little bit destructive here, but that's fine. So we looked at sorting operations. We really briefly looked at the selection sort or insertion sort last semester. We're going to get back to those again here. We did the selection sort when we're playing with our positional linked list. So go find the smallest thing, put it here. Find the next smallest thing, put it here. Find the next smallest thing, put it here. Find the next smallest thing, put it here. Right? It's n minus one, n minus two, n minus three. So that's n squared performance. Right? If it's n times n minus one times n minus two times n minus three plus, right? On and on and on. So we can get faster than that sorting by using a heap. So if I take a bunch of numbers and throw them in a heap, adding all those numbers was n times log n, right? N items had to be added at log n performance, and then I take them all out, right? To get them all out here, I get log of n performance, n times. So it's 2 n log n to add everything and remove everything to get a sorted list here. So log, and you throw away your constants, so we're still log of n. That's very exciting, isn't it?
Well, we probably needed to like, I understand the goal here, but decide how we're gonna sort it before we actually build this out.
So if we wanted to do it fast and easily, this list structure works really well. You can build it with the links. It's just awkward here. I'm not charging. What did I do here? I didn't plug in. My computer's about to die. I did plug in, didn't I? It's plugged in. No? Does that charger plug not work? I just noticed my computer's about to die. I'm like, oh crap. There it goes. Yeah, that plug is bad. Okay. I was at 11%. There we go. So you could build these queues with the linked structure, but really quickly we saw it got really messy because I had to like look if I had a left, look if I had a right, and do all these sorts of things, and then how do I know where I'm going to go? Is we just know it causes trouble here. Again, we want easy solutions that are performant here. So this works out really well for us. So we could take advantage of that structure. Most trees can't be put into lists, but complete binary trees can, because I know I'm always going to add to that very next position, which is just the end of my list here as I go. Um, we'll go back to the links when we do our binary search trees because we can't guarantee it's in a particular form. So we'll come back to that idea, but we're going to look at it doesn't fit for this solution. Right? We're just here's a bunch of different tools to add to your toolkit. Here's a bunch of different ways of storing data. They're good at these things and bad at these things. So that's sort of I'll be able to work all those out. So let's give it a try here. Let me move this out to tree here. Cut that out here. This is a n tree here. And then we'll go back to main, n tree, import tree. Okay. Oh, n underscore tree. There we go. N under tree. Okay. And then from priority queue, import my max priority queue list-based version here. All right, and we'll leave all that other stuff here. So we can have a bunch of random numbers here. So for number in range, actually, really, it doesn't matter what we put in here. We'll do 100 numbers here. I don't actually need the number. So a lot of times you might see people use an underscore. That's sort of like, I'm going to throw this away. Um, import random. We'll take our queue. So we'll make a max priority queue. Um, priority queue, max queue is a max priority queue list here. And then we'll take max queue and we want to add random.randint 1 to 1,000. Right? We'll just pick a bunch of numbers here. We'll do 100 numbers, 1 to 1,000. And then while max queue, we didn't do a length. Shoot, we should add that in here. So we can have a length, define length here, return length of self.data. This makes that really easy. Having to count how many items are in a binary tree, it's a little bit tricky. We'll come back to that problem later because you've got to recursively check every single child and add them all up here. Like how many children do you have? How many children do you have? How many children do you have? Add them all up here. It gets to be a little awkward. Anyway, so while max q or the length of max q, and again, if it's not 0, it's true. So we can just stick this in a loop here. It looks a little awkward here in Python, but we're using that truthiness here. We'll print max q dot remove. So it should give me in max sorted order then 100 values from 1 to 1,000. Uh-oh, we broke it. What do we do here? Indentation error. Oh, do we never do remove max? Oh, that was in the priority queue linked here. That's why we never had that one here. This is pass. Here, we'll forget that. Okay, that should be fine then. Maybe now we'll run. I'm going to run main. Run main. All right. Uh-oh. List index out of range. We can't pop off. Is that when we're empty here? Bless you. Um, if we're, is that removing the very last item? What happened here? List index out of, oh, yeah, once we remove the very last item, it's gone here. So I guess we should check here. So, I don't know, item is self.data.pop. And if we're empty, then let's see. So if the length of self.data, oops, self.data at 0 equals the item.
Probably just do if sub that data, right? And then at the beginning, if nothing happens, you just return.
Checking
So
for,
you just check if it's there, and if it's there, then you do the operation. If not, you don't do anything at all.
well, the problem is I popped the last thing off and then I became empty.
Yeah.
And now I don't have an index 0 to assign to.
Okay.
Uh, so when you pop the last one off here, the last item, there is no index 0 to replace, right? I guess we could check that. Does that make sense?
Yeah.
Okay. Uh, hopefully that fixes it now. We go back to main and run it, rerun. Oh, deck is not defined. Did I not? Oh, I didn't import it here. That's fine. This is from collections, import deck. This is the other file here.
This is the fun part, right?
Yeah, all the debugging here. We should just vibe code it. All right, so we get all the numbers sorted here. And this was n log n to n log n, but we get to throw away coefficients because why not here? Constants, we get to throw away. Or they're coefficients, right? Is that the right term? Like for 2n, is 2 a coefficient? Or just a constant? I don't remember my math terms. Coefficient. You can throw them away. We don't care. Yeah, throw away the coefficients. So 2n log n is still n log n in terms of performance. So we can sort a bunch of things here pretty quickly by hand, right? Doing a selection sort and insertion sort is going to be much slower here, and we're going to be n squared. You're going to look at n items here. Can be bad. So that's the priority queue, which gets to be kind of fun here. So as long as we can check, hey, are you greater than, we can sort things here. That's sort of the idea. So in lab, we'll go and use a priority queue. We can make a custom class that as long as we've implemented the less than function or greater than function, we can put into here. Or we can make a min one and look at the changes here. It's not too many changes to do max versus min here. That's also another fun exercise we can do. All right, so how are we doing so far? So we've got through priority queues. Next week we'll do our lab, and then we'll come back for maps, hash tables, and skip lists. Well, mention skip lists, we won't do them. Uh, building a map is building out a hash table. So we'll actually do this one here. Hash tables are really cool. Again, another trade-off in performance for certain things here. This is we're going to build our own Python dictionary, which is kind of fun. Okay. All right. We'll come back to trees again when we get to search trees. Don't sweat it too much if they don't make a whole lot of sense. We'll spend more time with it as we go. Okay. All right. Thanks, folks.